What you're watching in this video is the real-time calculation of a system impulse response of an RC circuit without actually hitting the circuit with a potentially damaging impulse. The impulse response of a system is important because it completely describes the system, but we'll talk about that more a little later. This is the RC circuit that we're analyzing in real time, calculating its impulse response without actually hitting it with an impulse. By adjusting R2, the 500K trim pot, we can change the time constant of this circuit, and we can see the change in the impulse response. For those of you interested in the theory, we're using the cross-correlation method of determining system impulse responses. It can be shown that the impulse response of a system can be calculated by cross-correlating a random noise input with the resulting output. It can also be shown that discrete interval binary pseudo-random noise can be used as a test signal. Binary pseudo-random noise can be generated from maximum length shift register sequences. It has been demonstrated that by using the deterministic pseudo-random binary noise test signals, a unique simplified cross-correlation algorithm can be used to produce continuous real-time system impulse responses. To demonstrate this unique cross-correlation algorithm for continuously calculating a system's impulse response, we have developed a process identification application using an inexpensive A to D converter module. For this demo, we are using a $50 DataQ Instruments DI-148U USB analog to digital converter. The 148U also has digital outputs, and we use one for creating the binary pseudo-random test signals. The control application for this demonstration process identification tool was developed by Charles Williams in VB.net. It provides setup options for the pseudo-random sequences, captures the test system's output data, and calculates, stores, and displays the impulse response waveforms continuously. So let's take a look at a live demo of this process identification tool analyzing our simple RC circuit.
Okay, the circuit we're using here has just classic RC circuit with a damped exponential response. There's a 10K here in the input leg and a 0 to 500K trim pot in parallel with a 220 microfarad capacitor that we can vary and change the time constant. The impulse response function is the 1 over R1C e to the minus R1 plus R2 over R1 times R2 times C t. This gives a damped exponential, and as we change R2, we can change the settling time of the impulse response, and we will see that as we decrease R2, we'll see the settling time settle faster, and as we increase R2, we'll see it settle slower.
The first thing we do in the control panel after initializing the A to D converter is to select a sequence length. In our demo, we will be using PN8, which is a sequence of 2 to the 8th minus 1 or 255 bits in length. The control panel also provides a feature to average the output calculated sequences. This reduces the signal to noise ratio. In our case, we have set it to average 2 runs. Next, we specify an output file to store the data being collected after each run. The get signal delay settings determine the noise sequence bit width and when, during each bit time, the test system's output is sampled by the A to D converter. There is a system output section in the control panel where specific information about each run and various calculated parameters from the averaged impulse responses are continuously displayed. 3 waveform charts are continuously displayed by the application. The cross-correlation waveform calculated during each run, the average cross-correlation of each sequence of runs, and the test system output waveform that is being sampled by the A to D converter. Each of these displays can be separately turned on or off with checkboxes on the control panel. So now we can press the Start Sequence button and view the calculated impulse response waveforms. You will notice that the cross-correlation method requires one complete pseudorandom sequence to be injected into the test system before the calculated impulse response waveform will be accurate. This requirement is easily verified by reviewing the calculus involved in the cross-correlation theory. After adjusting the trim pot on R2, the expected longer settling time of the impulse response is displayed.
Is that one settling earlier?
Not yet. We still have one more. There we go. Okay. So that one settles at 4 seconds. Okay. I'm going to stop. And I'm going to crank the pot again. And I'm cranking it clockwise.
And one final adjustment of the trim pot yields an even longer settling time. The captured and calculated data is continuously saved by the application in a text file for additional analysis. Here we are taking an average cross-correlation data file and using the charting function in Microsoft's Excel to plot the data. Then we compare it with the real-time waveform produced by the VB application. So in summary, we have shown how the impulse response of a system can be determined without hitting it with a potentially damaging impulse. We demonstrated this by applying a relatively low-level pseudo-random noise test signal at its input and then used a unique simplified cross-correlation algorithm to calculate the impulse response. Details of the unique simplified impulse response cross-correlation algorithm are in the public domain and can be found in the Georgia Institute of Technology library, documented in the 1969 Electrical Engineering Master's Thesis entitled System Impulse Response from Digital Cross-Correlation of Additive Input Noise and Output Signal. The VisualBasic.net application used in this video was written by Charles Anthony Williams. The background music for this video was composed and performed by Patrick Bryan Williams.